So as we just talked about, magma is melted rock under the surface inside the crust. And when it cools, it makes rocks such as granite and basalt, which we talked about before. They have crystals, they are solid and dense. There are basically two types of igneous rock or volcanic rock, which we'll talk about in a couple weeks. Volcanic rock is also known as igneous. And so the two main types are intrusive, which means it forms inside the Earth's crust. The other type is extrusive, which forms outside the Earth's crust. Exactly. So this is like lava rock. It's magma that has come to the surface, and it dries much more quickly because it dries quickly, and therefore it has air bubbles in it, and it is less dense. And I will show you some examples of these that we had talked about before. The intrusive rock includes things such as granite, which is very dense. The extrusive rock includes, as you mentioned, lava rock, which is very light. Some of it actually floats. And then the extrusive rock can also include things. This is compressed from an ash flow, and so you can see the different things included there. The granite, the intrusive rock, because it cools slowly, it has crystals, depending on how slowly it formed. But granite is an igneous, a volcanic rock. So I'll pass those around and you can take a look at those. One other type of extrusive rock you may have heard of is called obsidian or volcanic glass. So there's a number of different samples coming around for you to look at. Hawaii, of course, is an area where a lot of studying volcanoes has happened. And because of that, some of the names for the extrusive rock we have are Hawaiian names. If you look on page 205 in your textbook, the two of the types of lava rock are pahoehoe, which is kind of ropey and soft and taffy looking, like this. And the other one is called a'a, which I like to think of as the sound it would make if you walked over the very pokey rock. The a'a is thicker. Okay, so the pahoehoe is runny lava, and it's going to look like this. It looks kind of like taffy. Here's an example of pahoehoe. You can almost imagine that it was just flowing and stopped. The a'a was much thicker, and so as it tried to flow, it made all these really pointy, rough areas. And as you read about, it's got a higher silica content, and so it doesn't flow as well. The next thing that you read about yesterday was the different types of volcanoes. There are three main types of volcanoes, and the names should give you a big hint as to what they look like. The three volcano types: cinder cone, shield volcanoes, and composite volcanoes. So the cinder cone volcano, as the name implies, is cone-shaped, And this is a picture from the textbook. I know you can't really see it very well here. The cinder cone volcano is very triangular, and they're generally made up of a lot of little cinders or rocks. They're generally fairly explosive. So that's the cinder cone volcano. Very steep sides, very triangular. It gives an example of Sunset Crater in Arizona. You will see some other examples that I think are better examples than that one. And yes, I colored it these colors to cinder cones. Cinders are generally black like coal. The shield volcano is shaped like a shield. It's made from the runny or quiet eruptions over and over and over, making a really big, broad volcano like this. And then the third type is composite. A composite is something that's made up of more than one thing. The composite is, as you might expect, it has alternating layers of the cinders and then a runny lava eruption and then more cinders or explosive eruptions. And so what you end up with is a big lumpy shaped mountain. This is Mount St. Helens here. There's a big lumpy shaped mountain. That's actually kind of when it was erupting. We have some other pictures here as well, though. This one here is also Mount St. Helens before the eruption. So you can kind of see, kind of cone-shaped, but lumpy and more broad than the very narrow triangular cinder cone. So let's look at the two types of eruptions. One is the pyroclastic or explosive eruption. It's high viscosity, very thick rock, very thick lava. And what happens is the pressure builds up and builds up and builds up until it just absolutely explodes. And so as you see here, this is Mount St. Helens as it was exploding. This one here, and I know this is a really tiny picture, this is Mount Pinatubo, which is in the Philippines. And it's just a whole wall of this hot gas and ash. So let's see. It's a very sudden and violent eruption. There is hot gas and ash, and we'll see some of this in the video. And it travels incredibly fast, almost at the speed of sound, and basically wipes out everything in its path. It knocks down trees, it incinerates things, and if you don't have warning, this picture is in the textbook, I think on like 226 or something. There's actually a little Jeep right here trying to outrun it. And that was one that was pretty well studied. Then the second type of eruption, and then I'll get your questions, is the runny lava or effusive, or I think the textbook calls it quiet eruptions. And so what's happening here is the pressure is constantly being released. Lava is constantly coming out. And so you don't have, it's a little more predictable just because it's erupting all the time. Still very hot, still very dangerous, but it's not the sudden violent killer that the other ones are. And so this is like what you see in Hawaii. This is actually a picture from Hawaii. And really, when most people talk about volcanoes, this is what they are talking about. This picture here has kind of a cinder cone volcano. You see what you might have read about yesterday, this magma chamber building up in the bottom. And you'll see this also on the video. It builds up pressure. If there's not a good way for it to escape, it builds up and then explodes violently. If there are open vents, it just kind of oozes and runs out. Somebody asked about Yellowstone. At Yellowstone, what's happened, and the textbook has a really nice picture of Crater Lake, which is a volcano that's in Washington State. What happened is it exploded and exploded, and then finally the magma chamber just empties out and blows all the material out, and then you have this giant crater that collapses. Yeah, giant crater that collapses like this. And so it's huge and empty. And what Yellowstone is, it's a caldera like that, but now there's magma building underneath it again and starting to press up. All right, let's stop there for a second, and then we'll go over where they form, and then a few minutes of the video. This next page is a bit of a review. Oh, wait, that's just more pictures. These are the same pictures we just looked at. Mount St. Helens was composite, and then you can see the big crater. This is where it blew out, and there's a new cinder cone forming in the middle. And it is still active, little eruptions, lava and cinders coming out, not so dangerous now that the big eruption already happened. This is Mount Fuji. And when I look at that, to me, it looks like a composite volcano because it's so massive. The textbook says it's a cinder cone, which doesn't really make sense to me, so I'm not sure about that. Yeah, the composite ones are the alternating layers of eruptions. And as far as I know, Mount Fuji has had a lot of eruptions in the past. This is, again, Mount Pinatubo. Again, you see the little Jeep running away. They'd been studying this. There's a military base near that, and so they had been studying it to the last second. They evacuated everybody else. Yeah, they did get away. And this, again, this seems backwards to me. This is Mount Mayon in the Philippines, which I know some of you are doing your report on. This says it's a composite volcano. This, to me, looks more cinder cone. But you can see by the cutaway that it's been active over many years, and you can see the different types of eruptions. And then the Shield volcano, again from the textbook. This is Hawaii, and that says cinder cone there. But this is Hawaii here. All right. And then a bit of review. The first section you read yesterday talked about where do earthquakes occur. The three main, they occur at 2 of the 3 plate boundaries, divergent and convergent. They do not occur at the transform boundaries. And where do we see volcanoes at the divergent boundaries? Divergent, which is moving apart. So that would be at the mid-ocean ridge, right? That volcanic activity is what's pushing the 2 plates apart. We will see in the video the volcano in Iceland, which is a big example of this. It erupted in 2010, and I'm not going to pronounce the name of the volcano, but they pronounce it in the video, so you can watch for that. So this here, it's coming up and continuing to push these apart. And then at the convergent boundaries, where the 2 plates are moving together, as you guys mentioned, when you get the subduction zone, so here they're moving together. This one's moving this way, this one's moving that way, and as this plate pushes down into the mantle and starts melting, it creates enough heat and pressure, you get lava coming up here. Mountains like that are like Mount St. Helens, or if it happens under the ocean, then you have what's called an island arc, and I believe this is what's happening in the Philippines and possibly even in Japan, but the subduction zone where you're getting a lot of volcanic activity. And then finally, we have hotspot volcanoes that are not happening at a plate boundary. And so, for instance, the very famous volcanoes of Hawaii are not at a plate boundary, so they're kind of not following the rules from one of the most famous earthquakes. And what's happening here, it's called a mantle plume. And there's just a very active place in the mantle that is literally burning a hole through the crust. And here in Hawaii, you can see as the Pacific plate is moving to the north, you see the active area is at the south end of the volcano chain. And this is what they do believe is also happening at Yellowstone, is that there's a very active area under the North American plate there. Because it is, again, in the middle of a plate, not at a plate boundary.